tonight. Voyager 1 is so far from Earth that even light is beginning to feel slow. The spacecraft left this planet on September 5th, 1977. Its 49th anniversary is still a few weeks away, but after almost 49 years of uninterrupted flight, it has become the most distant human-made object in existence. Right now, it is roughly 171 astronomical units from the Sun, more than 25 billion kilometers away, and still moving outward at about 17 kilometers every second. A radio message sent toward it needs nearly a full day to arrive. By November 18, 2026, NASA calculates that Voyager 1 will cross an extraordinary threshold: 1 light day from Earth, 1 command out, 1 day of waiting, then nearly another day before any reply can come home. But that still does not really answer the question. Where is Voyager 1? Not just how many kilometers away. What surrounds it? What direction is it moving? Has it actually left the solar system? And after all this time, how can a machine built before the first space shuttle flight still tell us anything from that darkness? Before we go farther, if you enjoy journeys like this, like the video, subscribe, and leave a comment with the place in space you want us to track next. Because Voyager's location is stranger than one number on a map, the simplest answer is that Voyager 1 is in interstellar space, beyond the heliopause, the outer boundary of the enormous bubble created by the Sun's solar wind. It crossed that boundary in August 2012 at about 121.6 astronomical units from the Sun, becoming the first spacecraft to directly sample the environment outside the heliosphere. That was not a symbolic line drawn by astronomers after the fact. Voyager measured the change. Particles associated with the Sun dropped sharply. Galactic cosmic rays rose. Plasma measurements later confirmed that the density around the spacecraft matched the interstellar medium rather than the solar wind. The machine had crossed from a region dominated by material flowing outward from our star into matter between the stars. And yet saying Voyager has left the solar system is only partly true. This is where the map breaks. If we define the solar system by the Sun's wind and magnetic bubble, Voyager 1 is outside it. If we define the solar system by the region gravitationally bound to the Sun, Voyager is nowhere close to the end. Far beyond the planets lies the distant Oort cloud, a vast reservoir of icy bodies that may extend tens of thousands of astronomical units from the Sun. NASA estimates the Voyagers may need roughly 300 years just to reach its inner edge. Crossing the full region would take vastly longer. So Voyager is already traveling through interstellar matter while still moving through a domain that belongs, gravitationally, to the Sun. Both statements can be true. That distinction matters because there is no hard wall surrounding our planetary system. Space changes by layers. The planets end. The solar wind weakens. The wind becomes subsonic. The heliosphere gives way to interstellar plasma. Farther out, the Sun's gravity still holds distant objects in slow orbits. Voyager 1 has passed one major frontier. Not every possible frontier. Now picture its direction. The planets orbit the Sun inside a broad, nearly flat plane called the ecliptic. Voyager 1 is not following that plane outward like a car continuing along a highway. Its encounter with Saturn threw it onto a steep escape trajectory. It is moving about 35 degrees north of the ecliptic, generally toward the constellation Ophiuchus and in the broad direction of the solar apex, the direction the Sun itself moves relative to nearby stars. At roughly 3.5 astronomical units per year, Voyager is not circling back, it is escaping. There is another trap hidden inside the phrase, right now. We never see Voyager 1 right now. When a signal reaches Earth, it is already a report from almost a day ago. The spacecraft transmits an extremely weak radio beam toward the deep space network, and those radio waves travel at light speed. Distance has turned every measurement into history. If an engineer sends a command tonight, Voyager will continue doing whatever it was already doing for nearly a day before that instruction even reaches it. If the spacecraft then responds, Earth waits almost another day for the answer. Soon, the round-trip conversation time will exceed 2 full days. NASA says Voyager 1 will reach exactly 1 light day from Earth on November 18, 2026. That delay is not a communications flaw. It is the geometry of the universe becoming operational. And the distance keeps changing in a slightly surprising way. Voyager is steadily moving away from the Sun, but its exact distance from Earth does not increase as a perfectly smooth line. Earth itself is orbiting. Over the year, our planet moves roughly 1 astronomical unit to either side of the Sun relative to the distant probe. So the Earth to Voyager range gently breathes as our planet swings around its orbit while Voyager continues outward. There is a clean heliocentric distance from the Sun, and a slightly more complicated range from the moving Earth. Where is it depends on the reference point. The more astonishing fact is that Voyager is not merely a dead object whose position we calculate from an old trajectory. It is still an operating spacecraft. In April 2026, mission engineers shut down its low-energy charged particles instrument to conserve dwindling electrical power. Voyager 1 now has 2 science instruments operating, its magnetometer and plasma wave subsystem. Nearly every watt matters. The radioisotope generators that have powered the spacecraft since launch produce less electricity as their plutonium fuel decays, forcing engineers to turn off systems one by one to keep the remaining mission alive. So out beyond the solar wind, almost 1 light day away, an artifact from 1977 is still measuring magnetic fields and listening to plasma waves in a region no other functioning spacecraft has reached. That changes the meaning of its location again. Voyager 1 is not simply far away. It is our only active measuring point on that particular path through the local interstellar medium. Every new packet extends a map of interstellar conditions that no earlier spacecraft could draw from the inside. And this is where the real journey begins. Because once we know where Voyager is on a map, a much harder question appears. How did a spacecraft designed for Jupiter and Saturn end up on an escape path that will carry it between the stars for tens of thousands of years? The answer begins with a trick that sounds almost like cheating. Voyager 1 did not carry enough fuel to simply burn its way from Earth to Jupiter, then Saturn, then onward forever. It could not. The spacecraft was small, its propellant limited, and the outer solar system is brutally large. Instead, the mission used something far more powerful than an engine, the motion of the planets themselves. In the late 1970s, Jupiter, Saturn, Uranus and Neptune occupied a rare geometric arrangement that made a chain of gravity assists possible. This kind of alignment comes only about once every 175 years. Mission planners realized that a spacecraft passing a giant planet at exactly the right angle could have its path bent and its speed relative to the Sun increased, allowing the planet to hand the spacecraft onward toward the next world. More than 10,000 possible trajectories were studied before the Voyager routes were chosen. The mission was not simply launched into deep space. It was threaded through a moving gravitational machine. The phrase gravity assist can make the process sound mysterious, as if Jupiter somehow pulls a spacecraft in, whips it around, and throws it away with free energy. But no energy appears from nowhere. Voyager approached Jupiter while both spacecraft and planet were racing around the Sun. As Voyager fell into Jupiter's gravity, it accelerated. Relative to Jupiter, it eventually climbed back out with essentially the same speed it had before the encounter. Relative to the Sun, however, the direction of that velocity had changed, because Jupiter itself was moving. Voyager left carrying a tiny piece of the planet's enormous orbital momentum. Jupiter lost an immeasurably small amount of its own motion. Voyager gained enough to transform the mission. That is the first key to understanding where Voyager 1 is now. Its present motion was not created by one giant launch burn in 1977. It was built in stages by celestial mechanics. Voyager 1 launched on September 5, 1977, 16 days after Voyager 2, yet it took a faster, shorter trajectory and reached Jupiter first. On March 5, 1979, it made its closest approach to the giant planet. Jupiter did more than reveal itself through Voyager's instruments. Its gravity changed the spacecraft's future. NASA estimates that the Jupiter encounter increased the Voyager's speed relative to the Sun by roughly 35,700 miles per hour. That was the boost that made Saturn reachable on a practical timescale. And this is where the story stops being a simple outward tour. Because Voyager 1's path through Saturn was chosen for science, not for maximum distance, one target mattered enormously. Titan, Saturn's largest moon, was already known to possess a substantial atmosphere, making it one of the most intriguing objects in the solar system. Mission designers therefore committed Voyager 1 to a close Titan encounter. That decision gave the spacecraft an extraordinary look at the moon, but it came with a permanent trajectory consequence. The Titan geometry and Saturn flyby bent Voyager 1 sharply northward, out of the ecliptic plane where the major planets travel. After its closest approach to Saturn on November 12, 1980, Voyager 1 was no longer aimed toward Uranus or Neptune. The planetary tour was over. Its escape trajectory had begun. This matters because Voyager 1 and Voyager 2 were never just copies tracing the same road at Saturn. Their futures split. Voyager 2 took a route that preserved the possibility of continuing to Uranus and then Neptune. Voyager 1 sacrificed those worlds for Titan and was redirected above the planetary plane. The spacecraft that would eventually become humanity's most distant object did so partly because mission planners chose one moon over 2 planets. That is a strange trade when viewed from almost 5 decades later. We tend to imagine Voyager 1's interstellar journey as the ultimate objective, as if every decision had been made to send it as far away as possible. It was not. The original funded mission focused on Jupiter and Saturn. Interstellar space became the vast continuation after the prime planetary mission succeeded. The path into the darkness emerged from a sequence of choices made to extract the best science available at the time. Once Voyager 1 left Saturn, the character of the mission changed completely. There would be no next planet waiting ahead, no giant disk growing larger in the camera, no scheduled close encounter to reorganize the spacecraft's trajectory. The Sun would keep pulling backward, continuously slowing Voyager's outward motion, but not enough to bring it home. The spacecraft had already acquired sufficient heliocentric energy to escape. From then on, its route became an open curve leaving the Sun, rather than a closed orbit returning toward it. That distinction is enormous. Most objects we launch remain gravitationally bound. Satellites circle Earth. Many interplanetary spacecraft circle the Sun. Even a vehicle traveling billions of kilometers can still be on a path that eventually bends back inward. Voyager 1 is different. Its trajectory is hyperbolic with respect to the Sun. Barring some distant future encounter, it is not completing an orbit, it is leaving. But leaving does not mean moving through empty nothingness. For decades after Saturn, Voyager still traveled inside the heliosphere, immersed in the Sun's extended atmosphere of charged particles and magnetic fields. The planets disappeared behind it, but the Sun's influence did not. Voyager had escaped the architecture of planetary encounters long before it escaped the solar wind, that created a second mission, hiding inside the first one. Not a journey from planet to planet, but a journey through the Sun's outermost environment. And unlike the Jupiter and Saturn encounters, this new destination had no visible surface and no precisely known location. The boundary ahead could move. The solar wind expands outward at hundreds of kilometers per second, inflating a vast bubble around the Sun. Somewhere far beyond the planets, that wind begins to collide with the surrounding interstellar medium. The flow changes. The magnetic environment changes. Particle populations change. Eventually, the outward solar wind can no longer dominate the space around the spacecraft. But before Voyager arrived, no functioning probe had ever crossed that entire region. Scientists had models, they had estimates. They did not have a road sign telling them exactly where the solar system's plasma frontier would appear. So after Saturn, Voyager 1 entered a mission in which distance itself became an experiment. Every year outward tested how far the sun's invisible reach really extended. Every change in particles or magnetic fields became a clue. And what Voyager eventually found was not one clean edge waiting in the dark, but a sequence of physical transitions that forced scientists to decide what leaving the solar system actually means. That is the next part of its location story. Because long before Voyager 1 crossed into interstellar space, it encountered a boundary that changed the solar wind first. That first major boundary arrived in December 2004, when Voyager 1 was about 94 astronomical units from the Sun. By then, sunlight at the spacecraft was thousands of times weaker than it is at Earth. But light was not the important thing. The invisible solar wind was. For nearly 3 decades, Voyager had been traveling through that outward flood of charged particles. Close to the Sun, the wind moves faster than the local speed at which disturbances can travel through the plasma. In other words, it is supersonic. Farther out, resistance from the surrounding interstellar medium forces that flow to change. The place where it changes is called the termination shock. Voyager 1 crossed it first. A shock is not a solid barrier. Nothing struck the spacecraft. There was no flash, no wall, no sudden darkness. The change appeared in the behavior of particles and magnetic fields around the probe. The solar wind slowed dramatically and became hotter and more turbulent. Voyager had entered the heliosheath, the broad outer layer of the heliosphere, where the sun's wind was still present, but no longer expanding with the same freedom it had enjoyed closer to home. That gave scientists their first direct measurement of a region that had previously existed mainly in models, and the crossing immediately complicated the picture. Voyager 1 met the termination shock at about 94 AU. Voyager 2 would cross the same kind of boundary in 2007 at only about 84 AU. The difference showed that the heliosphere is not a perfectly centered sphere with one fixed radius. Its shape responds to solar activity, magnetic fields, and pressure from the interstellar environment outside it. The boundary can move. Different directions through the heliosphere can produce different distances. This is why asking for Voyager's location eventually becomes a physics question rather than a mapping question. Inside the heliosheath, Voyager 1 kept moving outward for almost 8 more years. The Sun was still behind everything the spacecraft measured, but its grip on the plasma was weakening. Scientists watched the flow of charged particles, they watched cosmic rays, they watched magnetic fields, and by 2010 something especially strange happened. The outward radial speed of the solar wind around Voyager fell to roughly 0. Think about what that means. Voyager itself was still escaping, but the solar material surrounding it was no longer streaming outward past the spacecraft in the familiar way. The wind had been compressed, slowed, and diverted as it approached the heliosphere's outer edge. Voyager was moving through a region where the sun's breath had effectively stopped advancing directly outward. That still was not the heliopause. The distinction became crucial. If mission scientists had treated the first dramatic change as the final boundary, they would have declared interstellar space too early. Instead, the instruments kept exposing intermediate states. The heliosheath was not a thin shell that Voyager could cross in a few days. It was an enormous physical environment in its own right, tens of astronomical units thick along Voyager 1's path. Then, in 2012, the particle data began changing fast. Voyager's detectors saw particles associated with the Sun fall away, while higher-energy galactic cosmic rays coming from outside the heliosphere surged. These cosmic rays are atomic nuclei and other energetic particles accelerated by violent processes elsewhere in the galaxy. The heliosphere blocks or deflects some of them. As Voyager approached its outer boundary, that protection weakened. The spacecraft was beginning to sample the galaxy more directly. By late July and August, the changes became dramatic. Solar particles dropped, recovered, then dropped again. Galactic particles rose. The boundary seemed less like a painted line and more like an unstable interface that Voyager was probing as conditions shifted around it. On August 25, 2012, the decisive particle transition occurred at roughly 121 to 122 AU from the Sun. But even then, the team did not immediately announce that Voyager 1 had entered interstellar space. One reason was the magnetic field. Models had led scientists to expect that crossing the heliopause might bring a substantial change in magnetic field direction. Voyager measured an increase in field strength, but the direction did not rotate as dramatically as expected. That was a problem. The particle evidence looked like an exit. The magnetic geometry looked more ambiguous. For months, the most distant spacecraft in history occupied a scientific category with no comfortable label. This is one of the most important parts of the Voyager story because it shows what exploration actually looks like. Nature does not have to respect the diagram in a textbook. A spacecraft can cross a real physical boundary and still produce data that challenge the boundary conditions scientists expected to see. The missing evidence eventually came from an instrument that could not directly measure the solar wind plasma itself. Voyager 1's dedicated plasma instrument had stopped working decades earlier, so scientists needed another way to determine the density of the material surrounding the spacecraft. The plasma wave subsystem provided it. Instead of counting the plasma directly, it could detect oscillations in the charged particles around Voyager. The frequency of those oscillations reveals electron density. Then the Sun provided the trigger. Powerful solar eruptions sent disturbances racing outward through the heliosphere many months later. Those disturbances reached the region around Voyager and excited the local plasma. In October and November 2012, and more clearly in April and May 2013, the spacecraft detected plasma oscillations at frequencies corresponding to a much denser environment than the outer heliosheath. The density was consistent with interstellar plasma. That measurement changed the verdict. Scientists could work backward from the density trend and the earlier particle changes. The evidence pointed to August 25, 2012 as the crossing date. Voyager 1 had passed the heliopause. The spacecraft was in interstellar space. And the proof was almost poetic. Humanity did not recognize the crossing by photographing a border. We recognized it by measuring how an invisible sea of electrons vibrated around a machine more than 18 billion kilometers from the Sun. Yet even that famous crossing contains one more surprise. Voyager had entered interstellar matter. But the Sun had not simply vanished from the physics around it. Solar eruptions could still travel outward and disturb the plasma there. The magnetic field just beyond the heliopause could still be distorted by the heliosphere. The boundary separated two environments, but it did not create perfect isolation between them. Which means Voyager 1's present location is not merely outside. It is moving through the complicated interaction zone between our star's enormous magnetic bubble and the local material of the Milky Way. And to understand how strange that location really is, we have to ask what interstellar space around Voyager is actually made of. Interstellar space sounds empty. It is not. The region around Voyager 1 contains gas, dust, magnetic fields, energetic particles, and the faint remains of material shaped by generations of stars. The density is extraordinarily low by terrestrial standards, but it is still high enough to leave measurable fingerprints on the spacecraft. Voyager is not flying through a perfect vacuum. It is moving through the local interstellar medium, the thin material occupying the space between nearby stars. Most of that material is hydrogen. Some is neutral. Some is ionized. There is helium. There are traces of heavier elements. There are cosmic rays carrying enormous energies. There are magnetic fields far weaker than anything we encounter in ordinary life, yet strong enough to influence charged particles across astronomical distances. Taken together, these components create an environment that is almost impossible to reproduce at full scale in any laboratory. And Voyager is inside it. The spacecraft's plasma wave subsystem has become especially valuable here because it can infer the density of the plasma surrounding Voyager from the natural oscillations of electrons. The numbers are tiny. A typical cubic centimeter of interstellar space near Voyager contains only a fraction of an electron, yet that is still substantially denser than the extremely dilute plasma Voyager encountered in the outer heliosphere. That difference is one of the reasons scientists became confident that the spacecraft had truly crossed the heliopause. But the density did not remain perfectly constant. As Voyager moved farther into interstellar space, measurements showed gradual changes in the electron density around it. This told researchers something important. The material outside the heliosphere is not uniform. It has structure. It can be compressed. It can respond to disturbances traveling outward from the Sun. Even beyond the heliopause, Voyager continues to reveal that the boundary between solar and interstellar space is dynamic rather than cleanly separated. That is almost counterintuitive. We tend to imagine interstellar space as the place where the Sun finally stops mattering. Yet enormous eruptions from the Sun can launch shockwaves that continue moving outward long after they have passed the planets. When those disturbances reach the interstellar plasma near Voyager, they can compress it and trigger oscillations detectable by the spacecraft. The Sun can no longer dominate the bulk flow of material there, but its disturbances can still travel into the surrounding interstellar environment. So Voyager is outside the heliosphere, while still hearing echoes from the star it left behind. There is another major change outside the heliopause: cosmic rays. Inside the heliosphere, the solar wind and the Sun's magnetic field help shield the inner solar system from part of the galactic cosmic ray population. These particles originate far beyond our immediate neighborhood. Some are accelerated by supernova remnants and other violent astrophysical processes. They travel through the galaxy at enormous speeds and can carry enough energy to pass through matter with ease. Voyager 1 now encounters more of them directly. The spacecraft's cosmic ray subsystem measured a sharp increase in galactic cosmic rays near the heliopause crossing. At the same time, energetic particles associated with the heliosphere dropped dramatically. That exchange became one of the most recognizable signatures of Voyager's passage into a new physical environment. For the spacecraft itself, however, there is no sense of arrival. Nothing visually changed. If a camera were still operating and could somehow photograph the surroundings, the scene would remain almost completely black. The nearest stars would still look like stars. The Sun would appear as a very bright point, not a disk. There would be no glowing mist surrounding Voyager, no visible wall behind it, no dramatic cloud ahead. The most important features of the region are invisible to human eyes. This is one reason Voyager's current position is so difficult to imagine. At 25 billion kilometers, distance alone becomes abstract. But the deeper problem is that the landmarks have disappeared. Near Earth, location is intuitive. We can describe altitude, longitude, oceans, continents, cities. Inside the planetary system, location can still be anchored to worlds. Near Jupiter, beyond Saturn, crossing Neptune's orbit. Voyager 1 has moved beyond that kind of geography. Its surroundings are described by particle density, magnetic field direction, solar distance, plasma oscillations, cosmic ray intensity, and velocity vectors. The farther it goes, the less useful ordinary visual language becomes. Even its distance from the planets is no longer the main story. Neptune orbits the Sun at about 30 astronomical units. Voyager 1 is now more than 5 times farther from the Sun than Neptune is. Pluto's average orbital distance is roughly 39.5 AU. The spacecraft passed that scale decades ago. The entire familiar planetary system occupies only the inner portion of Voyager's journey. Yet Voyager has barely begun its journey on interstellar scales. This is the contradiction at the heart of the mission. Measured against human engineering, Voyager is almost unimaginably far away. Measured against the galaxy, it has gone almost nowhere. 1 light-year equals about 63,241 astronomical units. Voyager is only around 171 AU from the Sun. In nearly 49 years, it has travelled only a tiny fraction of 1 light-year. The nearest star system, Alpha Centauri, lies more than 4 light-years away. Even if Voyager happened to be travelling directly toward it, which it is not, the trip would take tens of thousands of years at the spacecraft's present speed. The same thing is true of the stars that appear to lie in Voyager's direction. From Earth, We can draw a line through the sky and say the spacecraft is heading generally toward a particular constellation. But constellations are projections. The stars that form them can lie at radically different distances. Voyager is not traveling toward a flat pattern painted across the sky. It is moving through three-dimensional galactic space. Over thousands of years, the stars themselves move. The Sun moves. Voyager moves. So predicting a distant stellar encounter requires tracing all of those motions forward together. NASA's trajectory calculations show that in roughly 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445, also known as AC plus 793888. Today, that star lies about 17 light-years from Earth in the constellation Camelopardalis. By the time Voyager passes it, however, Gliese 445 will have moved considerably closer to our part of the galaxy. Even then, 1.6 light-years is not a close encounter in the planetary sense. It is more than 100,000 times the Earth-Sun distance. Voyager will not enter a planetary system around the star. It will not photograph its worlds. It will not dramatically curve around it. It will simply pass through the same broad region of galactic space while remaining enormously distant. And long before that happens, Voyager will have gone silent. The spacecraft's electrical power is fading year by year. One instrument after another has already been turned off to preserve what remains. Eventually, there will not be enough power to operate the scientific instruments, heaters, communications hardware, and attitude control systems required to send useful data back to Earth. The machine will continue moving. The mission will not. That creates another strange boundary in the Voyager story, one that has nothing to do with the heliosphere. There will come a moment when humanity still knows where Voyager 1 should be, but can no longer hear it. Its trajectory will remain predictable for a very long time. Gravity will continue guiding it. The spacecraft will continue crossing interstellar space, but the live thread connecting it to Earth will end. And that thread is already astonishingly fragile. Because the signal Voyager 1 sends home begins with a transmitter producing only a few tens of watts, less electrical power than many household light bulbs, by the time that signal spreads across more than 25 billion kilometers and reaches Earth, it has become almost unimaginably weak. Yet we can still detect it, which leads to one of the most extraordinary parts of Voyager 1's present location. Not where the spacecraft is, how Earth can still hear something from that far away. Voyager 1's transmitter is not powerful. That is what makes the connection so remarkable. The spacecraft's radio system sends its signal through a high-gain antenna, only 3.7 meters across. The transmitter operates with power measured in the tens of watts. At Earth, that would be ordinary. Across interstellar distances, it is almost nothing. The signal spreads as it travels. Like ripples expanding across water, the radio energy becomes distributed over an ever larger area. By the time Voyager's transmission reaches Earth, the original beam has expanded across billions of kilometers. Only an extraordinarily tiny fraction of that energy lands on one of the giant antennas of NASA's Deep Space Network. The received power is so weak that it is measured in fractions of a billionth of a billionth of a watt. And still, information survives. NASA's Deep Space Network, or DSN, is a global system of enormous radio antennas located in California, Spain, and Australia. Those sites are separated across Earth so that as the planet rotates, at least one complex can communicate with distant spacecraft in different parts of the sky. Voyager 1 depends heavily on that network. Its antenna must remain pointed toward Earth with extraordinary precision. There is no technician beside it, no repair ship, no second spacecraft nearby to relay the signal. Voyager has to orient itself using its own attitude control system, fire tiny thrusters when necessary, and keep that narrow radio connection aligned with a planet that is no longer visually significant from its position. Earth is simply a direction, a tiny target in space. The spacecraft does not need to see continents or oceans. It needs to know where to point. When Voyager transmits, the Deep Space Network listens for a carrier signal buried beneath natural radio noise. The antennas collect that whisper. Sensitive receivers amplify it. Signal processing systems reconstruct the encoded data. The result can be a stream of scientific measurements, engineering telemetry, or information about the health of the spacecraft. But the farther Voyager travels, the harder that job becomes. Radio intensity falls with the square of distance. Double the distance, and the same transmitted power spreads across 4 times the area. Move 10 times farther away, and the signal received at Earth becomes about 100 times weaker. Voyager has spent decades moving in exactly that direction. Farther, weaker, slower to communicate. And yet communication has survived far beyond anything most of its original designers expected to manage routinely. The data rate tells the story. During planetary encounters, Voyager could return images and scientific observations at much higher transmission rates. Today, communication is dramatically slower. The spacecraft is no longer sending streams of photographs. Its cameras have been off since 1990, and current science instruments return relatively small amounts of data. That slower rate is not a failure. It is adaptation. When a signal becomes weak, engineers can lower the data rate and spend more time distinguishing meaningful bits from noise. The system trades speed for reliability. A slower transmission can be detected more confidently at extreme distance. This is the same basic principle that appears across deep space communications. More distance means fewer photons and less radio energy collected per unit time, so the conversation slows down. And then there is the delay. At Voyager's present range, a radio command sent from Earth takes nearly a day to reach the spacecraft. The response takes nearly another day to return. That changes engineering itself. If something goes wrong, there is no real-time troubleshooting. Engineers cannot send a command, watch an immediate reaction, then adjust. They make a decision. They transmit. Then the spacecraft continues existing in whatever condition it is in, while Earth waits almost a day for the instruction to arrive. Only after that can Voyager act. Only after that can its reply begin the long trip back. The result is a conversation stretched across roughly 2 days, and sometimes the message that comes back says something has failed. Voyager 1 demonstrated just how difficult this can become in late 2023, when it began returning unusable science and engineering data. The spacecraft was still responding to commands, which meant the radio link itself had not disappeared, but the information coming home no longer made sense. The problem was eventually traced to the flight data subsystem. One part of the spacecraft's memory had become corrupted, likely because a chip had failed. Engineers were dealing with hardware launched in 1977, operating farther from Earth than any other spacecraft, with no possibility of physical repair. So they did something extraordinary. They worked around the damaged memory from Earth. The affected software had to be reorganized and moved into different parts of functioning memory. Because no single remaining section was large enough to hold the entire code block, engineers divided the software into pieces, placed those pieces in separate locations, and modified references so the system could still operate correctly. Every major command required waiting for the radio round trip. No rapid testing, no immediate confirmation, just careful engineering followed by silence. Then, in April 2024, Voyager 1 returned recognizable engineering data again. Science data followed. The repair did not make the spacecraft young. It proved that a machine nearly half a century old could still be reprogrammed from more than 24 billion kilometers away. That achievement reveals something important about Voyager's present position. Distance is not the only enemy. Age is. The spacecraft's electronics have endured decades of radiation, temperature changes, power loss, and component degradation. Some thrusters have clogged, some heaters have been switched off, instruments have been retired, computers operate with technology that would be considered primitive by modern consumer standards. Voyager's computers do not have gigabytes of memory. They do not have megabytes in the modern sense. The spacecraft was designed when computer memory was precious, processors were slow, and software had to be exceptionally compact. Yet that simplicity may be part of why engineers can still understand it. The spacecraft's architecture is old but documented. Its commands are limited. Its systems are comparatively direct. There is no modern operating system layered beneath millions of lines of code. Voyager was designed for a mission in which every byte, watt, and gram mattered. Now those same constraints define its survival. Power is the most severe. Voyager 1 does not use solar panels. At its current distance, sunlight is far too weak for the kind of solar-powered architecture common nearer the Sun. Instead, it carries 3 radioisotope thermoelectric generators. Inside them, plutonium-238 produces heat through radioactive decay. Thermocouples convert part of that heat directly into electricity. There are no spinning turbines, no combustion, no refueling, just decay. That decay made Voyager independent of sunlight, allowing it to travel past Jupiter, Saturn, and eventually beyond the heliosphere. But the power output declines every year. The plutonium produces less heat over time, and the thermocouples themselves become less efficient. Mission engineers therefore live inside a shrinking energy budget. A few watts can determine whether an instrument survives another year. Heaters, once considered essential, have sometimes been turned off, only for instruments to continue operating at temperatures below their original qualification limits. Systems are prioritized. Science instruments are shut down strategically. Electrical loads are reduced. Nothing is wasted. The spacecraft is not operating in the same configuration it had at launch. It is being reduced carefully, year by year, toward the smallest set of functions that can still produce useful science and maintain communication. Eventually, there will not be enough power. No amount of software repair can change radioactive decay. That is why Voyager's final years are not defined by distance alone. They are defined by triage. Which instrument stays on? Which heater can be sacrificed? Which subsystem still earns its watts? And how long can engineers keep the spacecraft scientifically alive before the available electrical power drops below the point where meaningful operations are possible? That answer leads directly to Voyager 1's true countdown. Not how long until it reaches another star. How long until Earth hears its last signal? Voyager 1's final signal will probably not arrive with a dramatic announcement. There may be no clean moment when the spacecraft simply says goodbye. Instead, the end is more likely to emerge from the same process that has defined its survival for years. Less power, fewer instruments, tighter margins, longer recoveries, and increasingly difficult choices about what can remain alive. As of 2026, Voyager 1 is still functioning, but its scientific payload has been reduced to just 2 operating instruments, the magnetometer and the plasma wave subsystem. Its cosmic ray subsystem was turned off in February 2025. Then, on April 17, 2026, engineers shut down the low-energy charged particles instrument to conserve electricity. That experiment had operated almost continuously since launch. After nearly 49 years, a piece of Voyager's original scientific capability simply had to be sacrificed so the rest of the mission could continue. The reason is brutally simple. Voyager loses about 4 watts of available electrical power every year. 4 watts does not sound like much. But when a spacecraft is already operating close to its minimum survival margin, 4 watts is enormous. A heater may consume a few watts. An instrument may consume a few watts. A subsystem that seemed negligible decades ago can suddenly determine whether the spacecraft remains above the threshold where its fault protection systems begin shutting things down automatically. Voyager has entered an era in which individual watts are mission events. NASA saw exactly how narrow that margin had become during a planned maneuver on February 27, 2026. While Voyager 1 rolled to calibrate one of its instruments, onboard power levels fell unexpectedly. Engineers knew that if power dropped much farther, the spacecraft's undervoltage protection could begin switching off hardware by itself. Recovering from that kind of event would be complicated, slow, and risky at a distance where every command takes roughly 23 hours to arrive. So the team acted before the spacecraft had to. They shut down the low-energy charged particles experiment. That decision bought time. NASA estimated that turning it off would provide roughly another year of breathing room, while engineers worked on a more ambitious power-saving strategy. Internally, the team gave that strategy a memorable nickname, the Big Bang. The name sounds violent. The actual idea is careful. Instead of continuing to shave power away through isolated changes, engineers developed a plan to replace a group of powered functions with lower energy alternatives in a coordinated sequence. The objective is not to revive Voyager to anything like its original capability. That era is over. The objective is to keep the spacecraft warm enough, stable enough, and electrically healthy enough to continue returning irreplaceable science from interstellar space. That phrase, irreplaceable science, is important. Voyager's value does not decline simply because fewer instruments remain. In one sense, the opposite is true. Every kilometre outward takes Voyager into territory no functioning spacecraft has sampled before. The magnetometer continues measuring the magnetic environment beyond the heliopause. The plasma wave subsystem continues sensing plasma behaviour in the local interstellar medium. No fleet of newer probes is following behind to duplicate those measurements. There is only Voyager 1 on this path. Voyager 2 is also operating outside the heliosphere, but it left in a different direction and crossed the heliopause at a different location. Together, the two spacecraft provide humanity with two direct sampling points in an environment surrounding a heliosphere that is vast, asymmetric, and constantly interacting with the galaxy around it. When one Voyager stops measuring, that measurement line disappears. That is why engineers continue fighting for individual watts. But power is not the only countdown. Propellant matters too. Voyager needs tiny hydrazine thrusters to control its orientation. Without attitude control, its high-gain antenna could drift away from Earth. The radio transmitter might still function, the computer might still function, the power system might still function. None of that would matter if the antenna were pointed in the wrong direction. This is one of the strange vulnerabilities of deep space communication. A spacecraft does not need to explode to disappear. It only needs to stop pointing accurately. Voyager's high-gain antenna produces a narrow radio beam from more than 25 billion kilometers away. Earth occupies an almost absurdly small angular target. The spacecraft's attitude control system therefore performs tiny corrections to maintain communication. Over the decades, engineers have had to adapt those systems as well. Some of Voyager's original thrusters became less efficient because residue accumulated in extremely narrow fuel lines. The team responded by changing how often the spacecraft fires its thrusters, allowing it to drift slightly farther before making corrections. That reduces the number of firings and helps conserve the remaining useful lifetime of the propulsion system. Again, survival comes from accepting less perfection. Slightly larger pointing errors, fewer maneuvers, fewer instruments, less heat, lower power, lower data rates. The modern Voyager mission is an exercise in controlled reduction, and every reduction reveals how much redundancy was designed into the spacecraft in the 1970s. Consider what has already failed or been retired. The cameras are gone. The ultraviolet spectrometer is gone. The planetary radio astronomy experiment is gone. The cosmic ray instrument is now gone. The low-energy charged particle instrument is now effectively gone from science operations. The dedicated plasma instrument stopped functioning properly years ago. Yet Voyager 1 still sends meaningful measurements home because the mission was never dependent on one sensor, one computer, one mode of communication, or one perfectly functioning subsystem. It was built for uncertainty. That is part of the deeper reason Voyager has lasted this long. The spacecraft was designed before mission teams could casually rely on software updates, enormous onboard memory, high bandwidth communication, or computationally intensive autonomy. Its engineers expected long delays and limited resources from the beginning. So they built layers, redundant computers, backup communication modes, multiple thruster branches, fault protection logic, command sequences that could be stored and executed without immediate supervision. Voyager had to survive Jupiter's radiation environment, the cold near Saturn, years without physical maintenance, and communication across billions of kilometers. What nobody could fully design for was half a century. Materials age, electronics degrade, lubricants change, radiation accumulates, insulation becomes brittle, fuel line behavior shifts, power declines. Components that once had comfortable margins eventually operate near limits their designers never expected them to reach operationally. And yet the spacecraft keeps exposing one of engineering's strangest truths. Longevity is not the same thing as remaining unchanged. Voyager has survived because the mission itself has been repeatedly reinvented. After Jupiter, it became a Saturn mission. After Saturn, it became an outer heliosphere mission. After the termination shock, it became a heliosheath mission. After the heliopause, it became an interstellar mission. Now it is becoming something even more austere, a two-instrument observatory trying to preserve one final scientific connection between Earth and unexplored galactic space. That connection cannot last forever. The radioisotope generators will continue fading. No software patch can stop plutonium-238 from decaying. No clever maneuver can manufacture electrical power. Eventually, engineers will face a configuration in which there simply are not enough watts left to operate the required systems simultaneously. Perhaps another science instrument will be shut down first. Perhaps heaters will be reduced further. Perhaps communication will become intermittent. Perhaps a hardware fault will force the issue before the power curve does. NASA does not present a single guaranteed date for the final transmission, because spacecraft do not age according to perfectly predictable schedules. Voyager has already survived beyond many expectations. Its remaining lifetime depends not only on available power, but on the continued health of systems that have been operating for almost 49 years. NASA still described both Voyagers as functioning in April 2026. So there is no precise clock counting down to silence, only probabilities, margins, and a machine growing weaker while moving farther away every second. But when the final useful signal eventually comes, something important will happen afterward. Voyager 1 will not stop. The antennas on Earth may hear nothing. The spacecraft may no longer know how to orient itself. Its instruments may freeze. Its computers may lose power. Its transmitter may fall silent permanently, but its velocity will remain. Gravity does not care whether the spacecraft is operating on. Voyager will continue moving through the Milky Way long after the mission ends, and that silent phase will last incomparably longer than the active one. The spacecraft has spent almost half a century communicating with Earth. Its next chapter could last billions of years, because once the final watt is gone, Voyager 1 becomes something fundamentally different. Not a mission, not an observatory, not even, in any practical sense, a spacecraft. It becomes an artifact moving between the stars. And attached to that artifact is one object designed for a future so distant that nobody who built Voyager expected to witness its purpose fulfilled. A record, a message, a fragment of Earth intended for whoever, or whatever, might someday find it. The Golden Record was never designed as a message Voyager 1 could deliver on schedule. There is no destination address, no known civilization waiting ahead, no star system that the spacecraft is deliberately approaching. The record exists because once Voyager escaped the planet, its trajectory became effectively permanent on human timescales. Long after its transmitter failed, long after its power disappeared, long after every working component had become inert, the spacecraft itself would continue. That made Voyager something unusual. A scientific instrument with an archaeological future. Mounted to the exterior of both Voyager spacecraft is a gold-plated copper phonograph record 12 inches across. Its official name is simply the Voyager Golden Record. The contents were assembled in 1977 by a committee led by astronomer Carl Sagan. The goal was not to summarize Earth perfectly. That would have been impossible. The goal was to create a compact introduction to this planet, its life, its environments, and the species responsible for launching the spacecraft. The record contains greetings in dozens of human languages, natural sounds from Earth, music from different cultures and eras, images encoded as analog information, scientific diagrams, human anatomy, animals, landscapes, architecture, food, mathematics, biology, and a sequence intended to communicate something more basic than any particular culture. We existed here. This was our world. And this machine came from us. There is something almost absurd about the scale mismatch. Voyager 1 is racing through interstellar space at around 17 kilometers per second. That feels fast until we compare it with the distances between stars. At that speed, 1 year of travel moves the spacecraft only a little more than 3.5 astronomical units farther from the Sun. 1 light year spans more than 63,000 astronomical units. The Golden Record was attached to a spacecraft that could survive physically for extraordinarily long periods, but that moves slowly compared with the geometry of the galaxy. Its next remotely notable stellar passage will not happen for roughly 40,000 years. And even that will not be a rendezvous. Voyager 1 is expected to pass within about 1.6 light-years of Gliese 445. That is close only by galactic standards. If the spacecraft passed our Sun at that distance today, it would still be tens of thousands of astronomical units away. You would not call that a visit. You would barely call it a neighborhood. So the chance that the Golden Record will ever be recovered by an extraterrestrial civilization is unknowable and probably very small. But that was never the only point. The record also changes how we understand Voyager itself. Because the spacecraft carries 2 different kinds of information, one stream moves backward. The radio signal, measurements flow from Voyager toward Earth, telling us about magnetic fields, plasma waves, spacecraft health, and interstellar conditions. The other stream moves forward. The Golden Record. It cannot transmit anything. It simply travels with the spacecraft. One message is alive only while the power system works. The other does not require electricity at all. That makes their timescales radically different. Voyager's radio mission may end within years. The physical spacecraft could persist for geological spans of time. In interstellar space, there is almost nothing to erode it in the way rain, oxygen, bacteria, and weather destroy objects on Earth. Micrometeoroid impacts will occur. Radiation will alter materials. The surface will slowly degrade. But there is no atmosphere dragging against it, and no ocean corroding it. A dead Voyager could remain recognizable far longer than any civilization we know has existed. That possibility raises a strange question. Where will it actually go after the Sun becomes just another star behind it? The answer is more complicated than drawing a straight line through today's sky. Voyager 1 is leaving the solar system, but it is not leaving the Milky Way. Its speed relative to the Sun is nowhere near enough to escape our galaxy. The spacecraft will continue orbiting the center of the Milky Way, just as the Sun does. Not beside the Sun, not on exactly the same orbit, but still gravitationally bound to the galaxy. In other words, Voyager's interstellar journey is not a one-way trip into infinite emptiness. It is a new orbit inside a much larger system. The Sun moves around the galactic center at roughly hundreds of kilometers per second. Nearby stars follow their own paths. Giant molecular clouds drift, stellar associations disperse, spiral structure changes over millions of years. Voyager's relationship to everything around it will be transformed. The constellation patterns visible from Earth today will not survive. Some nearby stars will move closer, others will move away. The Sun itself will cross different regions of the galaxy. Voyager will do the same. And this is where predictions become increasingly uncertain. We can calculate the spacecraft's current trajectory extremely well. We know its velocity. We know the gravitational influence of the Sun and nearby stars. We can integrate those motions forward. But the farther into the future we go, the more small uncertainties matter. An unknown stellar encounter could alter the spacecraft's trajectory slightly. A distant gravitational perturbation could accumulate. The motion of stars themselves has measurement uncertainties. Over millions and billions of years, predicting one tiny object through the changing gravitational environment of the galaxy becomes less like tracing a railway track and more like projecting a drifting grain through a moving ocean. Still, one thing is clear. Voyager will remain a galactic object. It will not simply fly out of the Milky Way. The spacecraft's roughly 17 km/s heliocentric escape speed is impressive only compared with planetary motion near us. Escaping the galaxy from the Sun's neighborhood would require vastly greater speed. Voyager is free of the Sun's planetary system. It is not free of the galaxy. And the galaxy will outlive the spacecraft's active mission by an almost incomprehensible margin. In roughly 5 billion years, the Sun will exhaust hydrogen in its core and begin evolving into a red giant. By then, Voyager could have completed many journeys around the Milky Way. Its original launch site will be unrecognizable. Earth itself may no longer resemble the planet represented on the Golden Record. Even the Sun will have changed radically. Voyager, if it survives physically, will be an artifact from a solar system that no longer exists in its present form. That is what makes the Golden Record so unusual. It is often described as a message to aliens, but in another sense, it is a time capsule with no scheduled opening date. Most time capsules are buried with the assumption that somebody from the same civilization will eventually recover them. Voyager offers no such guarantee. Its intended reader does not exist in any known plan. The record might travel forever without being found. Its encoded images might never be reconstructed. Its greetings might never be heard. Its music might never play again. And still, it serves a purpose now. It forces us to confront Voyager not just as a machine extending outward, but as a piece of Earth becoming physically separated from Earth forever. Every second, that separation increases by kilometers. Every hour, tens of thousands more. Every year, hundreds of millions. There will never be a recovery mission. Voyager is not coming home. But the strangest part of its journey is not that it carries a message into interstellar space. It is that Voyager may remain intact long after every person alive today is gone, while its exact location continues to move through a galaxy that is itself constantly changing. So if we really want to know where Voyager 1 is going, we have to zoom out one final time. Past the planets, past the heliosphere, past the nearby stars, and ask what happens to this spacecraft on the scale of millions, then billions of years. On the scale of millions of years, Voyager 1 stops looking like a spacecraft with a destination and starts looking more like a tiny artificial asteroid. Its engines will be silent. Its transmitter will be dead. Its instruments will no longer measure anything, but its momentum will remain. The spacecraft will continue moving under gravity through the Milky Way, passing through changing regions of interstellar gas and magnetic fields, while the stars around it slowly rearrange. That future is difficult to visualize because nearly every reference point we use today will be gone. The constellations will change. The Sun will move. Nearby stars will drift into new configurations. Voyager will continue following its own galactic path. For a while, we can still talk about relatively specific stellar encounters. Gliese 445 is the famous example. In roughly 40,000 years, Voyager 1 should pass within about 1.6 light-years of that star. But as we project farther forward, uncertainty grows. Stellar motions are not known with infinite precision. Small gravitational influences accumulate. The spacecraft itself could eventually pass closer to some object we cannot predict well today. Even so, the broad outcome is clear. Voyager 1 will remain bound to the Milky Way for an enormous span of time. It will orbit the galactic center, just as stars, gas clouds, and other debris do. One orbit of the Sun around the Milky Way takes on the order of hundreds of millions of years. Voyager will participate in the same vast galactic motion. That means the spacecraft's future is not a straight line through a static star field. It is a moving trajectory inside a rotating galaxy. Over hundreds of millions of years, Voyager could pass through very different galactic neighborhoods. It may cross regions with different gas densities. It may encounter stronger radiation environments. It may pass relatively near stars. It may spend unimaginably long intervals with almost nothing nearby at all. And during all of that time, the spacecraft itself will be aging physically. Interstellar space is gentle compared with Earth, but it is not harmless. Voyager will be bombarded by cosmic rays. Dust grains will strike its surface. High-energy particles will slowly damage materials. Microscopic impacts will crater metal. Radiation will alter the chemistry of polymers and coatings. Very small particles moving at high relative speed can produce disproportionately large damage over enough time. There is no maintenance. No shielding can remain perfect forever. No material is truly immortal. The golden record itself was designed with longevity in mind. Its gold plating helps protect the copper beneath it from corrosion. The record is covered by an aluminium protective case. Instructions explaining how to play it are etched onto the cover. A sample of uranium-238 was included as a kind of radioactive clock, offering a hypothetical finder a way to estimate how much time had passed since launch. The design assumes that any discoverer would not understand our languages or technology. So the instructions rely on physical constants. The transition of neutral hydrogen is used as a reference for units of time and length. The playback speed is encoded. The method for reconstructing the stored images is shown. A pulsar map indicates the location of the Sun relative to 14 pulsars and the center of the galaxy. That map is one of the most ambitious pieces of the message. Pulsars spin with highly characteristic periods. Those periods change predictably over time. In principle, a technically capable finder could measure the current periods, compare them with the values encoded on the record, and estimate both where the spacecraft came from and how long ago it left. But even that map has an expiration date. Pulsars evolve. Their rotation rates change. Some may stop behaving as detectable pulsars. Galactic motions shift positions. Over very long timescales, the map becomes harder to interpret. Nothing about the message is truly eternal. Not even the coordinates. That is the paradox of Voyager. It was designed to outlast its mission, but not time itself. On a million-year scale, it may remain recognizable. On a 100-million-year scale, perhaps still. On a billion-year scale, predicting the condition becomes far more speculative. A large collision could destroy it. A close stellar passage could alter its orbit. Radiation and impacts could erode exposed surfaces. The spacecraft might survive as a fragmented object rather than an intact machine. Or it might remain astonishingly well preserved. We cannot know, but there is another future event that places Voyager in an even stranger context. The Sun itself will not remain as it is. In about 5 billion years, the Sun will leave the stable, main sequence phase of its life. Its core hydrogen supply will become depleted. The core will contract. The outer layers will expand. The Sun will evolve into a red giant. The inner solar system will be transformed. Mercury will be destroyed. Venus will almost certainly be engulfed. Earth's ultimate fate is more complicated. but its present habitable state will be long gone, well before the red giant maximum. The Sun will eventually shed much of its outer material. What remains will contract into a white dwarf. That entire stellar evolution will occur while Voyager, if it still exists, continues somewhere else in the Milky Way. The spacecraft will have outlived the current form of the star that launched it. That is difficult to absorb. Voyager was built by people who measured its mission in years. The spacecraft itself may persist across a timescale on which stars evolve. The Sun could become a white dwarf, while an inert human artifact still circles the galaxy. But Voyager will not be alone in that future. Voyager 2 is also escaping. Pioneer 10 and Pioneer 11 are escaping. New Horizons is escaping. Each follows a different path into interstellar space. None is likely to encounter another closely. They are separating into the galaxy like fragments thrown from one tiny planetary system. Over enough time, their physical relationship to Earth becomes almost meaningless. They become independent orbiting debris. And this reveals something important about the phrase, "Where is Voyager 1 right now?" The answer depends entirely on the scale you choose. At human scale, it is impossibly far away. At solar system scale, it is just beyond the heliosphere. At stellar scale, it is still almost beside the Sun. At galactic scale, it has barely moved. And on cosmological scales, Voyager's entire journey is essentially zero. This is why the distance feels so contradictory. 25 billion kilometers is enormous enough that no person has ever traveled even remotely close to it. Yet 25 billion kilometers is only about one light day. The nearest star is more than 4 light years away. The Milky Way is roughly 100,000 light years across. The observable universe spans tens of billions of light years. Voyager has spent nearly half a century reaching a distance that light crosses in about one day. That comparison does not diminish the achievement. It reveals the size of the universe. Voyager is one of the fastest objects humanity has ever deliberately sent away from the Sun, and the galaxy still makes it look almost stationary. That scale gap also explains why no plausible extension of Voyager's current mission could turn it into a true starship. Even if its systems lasted indefinitely, the travel time between stars would remain enormous. At roughly 17 kilometers per second, Voyager would need around 70,000 years to travel the distance separating the Sun and Alpha Centauri if it were moving directly toward that system. Modern engineering can imagine faster concepts. Nuclear propulsion, fusion, laser-driven sails, antimatter concepts. But Voyager belongs to a different category. It is not a prototype interstellar vehicle. It is an interstellar survivor. It reached interstellar space not because it was designed to cross the distances between stars, but because planetary gravity gave it enough velocity to escape the Sun, and then time did the rest. That may be its most important lesson. Interstellar does not necessarily mean traveling to another star. It can simply mean crossing the boundary where the Sun's wind gives way to the galaxy beyond. Voyager 1 has done that. It is there now. And before we finish this journey, one final question remains. If Voyager is already in interstellar space, more than 25 billion kilometers away, and still barely separated from the Sun on a galactic scale, then what would its location actually look like if we could somehow stand beside it and look back toward home? Standing beside Voyager 1 would probably feel less dramatic than almost any image of deep space suggests. There would be no visible border behind you, no glowing shell marking the heliopause, no river of plasma flowing past, no bright band announcing that you had entered interstellar space. The surroundings would look black, almost completely black. The stars would appear intensely sharp because there would be no atmosphere to blur them, but their pattern would still look broadly familiar. Voyager is far from the planets, yet not far enough to transform the stellar sky dramatically from our point of view. The sun would no longer look like the disk we know. It would look like a star. A very bright one. At roughly 171 astronomical units, sunlight reaching Voyager is weakened by the inverse square law. Compared with Earth, the intensity is tens of thousands of times lower. But the sun would not disappear. It would remain overwhelmingly brighter than the surrounding stars. Earth, meanwhile, would be effectively invisible to the unaided eye. Not because Earth has ceased to exist as a meaningful object, but because scale has crushed it. Our entire planet is only about 12,700 kilometers across. From more than 25 billion kilometers away, that diameter occupies a vanishingly small angle. Even the orbit of Earth around the Sun would appear tiny. This is perhaps the most psychologically difficult part of imagining Voyager's location. From Voyager's perspective, nearly everything that defines human geography has collapsed into one direction. Earth. The Moon. Every city. Every ocean. Every person. Every telescope listening for Voyager's signal. All of it lies within a microscopic region around one bright star. The spacecraft has travelled far enough that the solar system itself begins to compress visually. That effect had already become apparent decades ago. On February 14, 1990, Voyager 1 turned its cameras backward toward the solar system and captured a famous series of images known as the Solar System Family Portrait. Earth appeared in one of those frames. A tiny point, less than a pixel, the pale blue dot. At the time, Voyager was only about 40 astronomical units from the Sun. Today, it is more than 4 times further away. If the same kind of image could be taken now under ideal conditions, Earth would be even more deeply lost in the Sun's glare and distance. But Voyager cannot take that photograph. Its cameras were deliberately shut down after the family portrait. There was little scientific reason to keep them powered. Beyond the planets, there were no nearby worlds to image. The mission's priorities had shifted toward particles, plasma, and magnetic fields. The camera system consumed power, so it was turned off. That decision is symbolic of the entire interstellar mission. As Voyager went farther, seeing became less important than sensing. The environment outside the heliosphere is not best understood through visible light. It is understood through invisible quantities: particle density, magnetic orientation, plasma frequency, cosmic ray intensity, radio propagation. If you were beside Voyager with human senses alone, you would miss almost everything the spacecraft is there to measure. You would not feel the plasma. You would not see the magnetic field. You would not notice the cosmic rays until some of them pass through your body. You would not perceive the difference between the heliosheath and interstellar medium the way Voyager's instruments can. To human senses, both would look like vacuum. To physics, they are different environments. That contrast explains why Voyager remains scientifically useful even though it has no functioning camera. Its location is valuable precisely because it is embedded in a region no telescope on Earth can directly sample in the same way. Astronomers can observe interstellar gas remotely. They can study absorption lines. They can infer magnetic fields. They can model the heliosphere. But Voyager is physically there. Its instruments respond to the particles surrounding the spacecraft itself. That is a fundamentally different kind of knowledge. Local measurement. In situ science. A machine inside the phenomenon. And the farther Voyager travels, the more important that distinction becomes. The heliopause is not the final destination because the region beyond it is not uniform. Voyager has already detected changing plasma densities. It has measured shocks propagated outward from solar activity. It has encountered persistent interstellar magnetic fields. The spacecraft is gradually building a radial profile of conditions beyond the heliosphere, a profile that did not exist before. But even radial can be misleading. Voyager is not simply measuring distance from the Sun. It is moving through one particular direction in a 3-dimensional environment. If the heliosphere has a complex shape, Voyager samples only one path through that shape. Voyager 2 samples another. Future probes could produce completely different crossing distances and environmental transitions, depending on where they leave. That means our current picture of the heliosphere is based partly on just two narrow tracks through an object billions of kilometers across. Two needle holes through an enormous structure. This is one reason scientists are cautious when drawing simple diagrams of the heliosphere. The familiar textbook image often resembles a comet. A rounded nose facing into the local interstellar flow and a long tail extending behind. But modern observations and models suggest the geometry may be more complicated. Magnetic fields matter. Solar variability matters. The surrounding interstellar medium matters. Different particle populations behave differently. Some models suggest a more compact shape. Others emphasize tail-like structures. The exact global geometry remains an active area of research. Voyager provides local truth inside that larger uncertainty. Wherever the global boundary lies, Voyager crossed it. Whatever the heliosphere's full shape turns out to be, the plasma around Voyager now has interstellar characteristics. That is why one spacecraft can be both a historical artifact and a continuing scientific experiment. Its position is not merely farther out. It is strategically unique. There is another way to understand how far away Voyager really is. Imagine compressing the solar system. Let Earth orbit just 1 meter from the Sun. On that scale, Jupiter would orbit a little over 5 meters away. Saturn would sit near 10 meters. Neptune would be around 30 meters from the Sun. Voyager 1 would be more than 170 meters away. That sounds substantial. But the nearest star would be more than 60 kilometers away. Suddenly, Voyager's achievement and its limitation become visible at the same time. It has crossed far beyond the planetary zone, and it has barely begun the distance between stars. If instead we scale the Sun-Earth distance down to 1 centimeter, Voyager is only about 1.7 meters from the Sun. Alpha Centauri is more than 600 meters away. The galaxy becomes absurdly larger still. This is the mental correction Voyager forces on us. The solar system is not small. Interstellar space is simply much larger. The spacecraft has reached the ocean. It has barely left the shore. And that makes the phrase, after 49 years, almost misleading. 49 years sounds like a lifetime. For a human being, it nearly is. For interstellar travel, it is a beginning. Voyager 1 has spent almost 5 decades converting speed into distance. Every second adds another 17 kilometers. Every minute adds roughly 1,000. Every hour, tens of thousands. Every day, more than 1 million. Every year, hundreds of millions. And still, the nearest stars remain overwhelmingly far away. That is the scale Voyager has entered. A regime where even uninterrupted motion for generations barely changes the galactic map. But there is one final way to answer where Voyager 1 is right now. Not with kilometers, not with astronomical units, not with light time, not with constellations, with relationship. Voyager 1 is beyond every planet, beyond the main influence of the solar wind, inside the local interstellar medium, still gravitationally tied to the Milky Way, still physically connected to Earth by radio, still carrying a map back to the world that launched it, and still moving away. The machine is farther from us than anything humanity has ever built. Yet every useful bit it sends home crosses that entire distance and ends here, on Earth. That is what makes Voyager's location more than a coordinate. It is a line. One end is a small spacecraft in interstellar space. The other is us. That line is still open. A signal leaves Earth, crosses more than 25 billion kilometers of space, reaches a spacecraft launched in 1977, changes what that spacecraft does, and then another signal begins the journey back. Nothing else humanity has built maintains a conversation across a greater distance. And the conversation is becoming stranger with time because Voyager 1 is not simply farther away each year, it is farther away in a region where the Sun itself is becoming less dominant. The spacecraft is now travelling through the local interstellar medium, but that phrase can sound as if Voyager has entered some vast uniform ocean surrounding the solar system. The reality is more complicated. The Sun is moving through the Milky Way. So is the interstellar material around it? The heliosphere exists because these two environments meet. The solar wind expands outward from the Sun. The surrounding interstellar medium presses inward from outside. Magnetic fields thread both regions. Neutral atoms can cross boundaries that charged particles cannot cross in the same way. Cosmic rays arrive from far beyond either system. The result is not a simple bubble suspended in empty space. It is an interaction. Voyager 1 is now on the outside of that interaction, moving through matter that belongs more to the galactic environment than to the solar wind. That gives its measurements a second value. Voyager is not only telling us what exists beyond the heliopause, it is helping us understand the shield around every planet we know. The heliosphere matters to Earth because it changes the radiation environment of the entire solar system. Galactic cosmic rays enter from outside. Solar magnetic fields and the solar wind modulate how many of those particles penetrate inward. When solar activity changes, cosmic ray conditions inside the heliosphere change too. Voyager can compare the environment outside that protective structure with measurements made closer to the Sun. That comparison helps researchers understand what the heliosphere actually does. And this question extends far beyond Voyager. Other stars almost certainly create their own astrospheres. Some may be enormous. Some may be compressed. Some may exist inside much denser interstellar environments than ours. The conditions surrounding a planetary system could affect the radiation reaching its planets. So by measuring the edge of our own heliosphere, Voyager is also helping build a physical framework for thinking about planetary systems elsewhere in the galaxy. A spacecraft launched to explore Jupiter and Saturn has become part of the study of how stars interact with interstellar space. That was not the original mission. It emerged because the spacecraft survived. This is one of Voyager's recurring patterns. The mission keeps outliving its own definitions. First, the goal was Jupiter, then Saturn, then the outer heliosphere, then the heliopause, then interstellar space. Now, simply continuing to exist produces science no replacement mission can yet reproduce. And there is a reason no replacement has arrived. Voyager's distance took nearly half a century to achieve. Launching something faster is possible in principle, but reaching 170 astronomical units still requires either extraordinary speed or extraordinary patience. New Horizons, for example, is also escaping the solar system after its Pluto encounter, but Voyager 1 remains much farther away. Other spacecraft have achieved higher speeds during portions of their missions, especially probes diving close to the Sun, where solar gravity accelerates them dramatically. But maximum instantaneous speed and long-term outward escape speed are not the same thing. Voyager has had decades to convert its roughly 17 kilometers per second of outward motion into distance. That is difficult to catch. If humanity launched another conventional deep space probe tomorrow, Voyager would have a lead measured in tens of billions of kilometers. A successor designed specifically for interstellar exploration would need to be much faster if scientists wanted it to reach the heliopause within a manageable scientific career. Researchers have proposed concepts sometimes described as interstellar probes. Not starships. Probes intended to travel several hundred or even 1,000 astronomical units from the Sun. Such missions could carry instruments designed from the beginning for the heliosphere's outer boundary and the nearby interstellar medium. They could measure plasma directly, map energetic neutral atoms, study dust, observe the solar system from far outside, potentially examine the heliosphere's global structure from a perspective Voyager was never designed to provide. But until something like that flies and survives the journey, Voyager remains alone at the frontier is opened. This makes every surviving instrument disproportionately important. A magnetometer aboard a spacecraft near Earth can be replaced. Another satellite can measure the same region. A magnetometer aboard Voyager 1 cannot. There is no second instrument a few million kilometers away taking equivalent readings. If Voyager's magnetometer stops functioning, that measurement at that location disappears. The same is true of the plasma wave subsystem. Its data may arrive slowly. Its hardware may be old. Its operating power may be tiny, but the environment surrounding it cannot currently be sampled by anything else. That gives the mission a kind of scientific scarcity. Not because the instruments themselves are uniquely advanced. They are not. Modern instruments can be vastly more capable. The scarcity comes from position. Voyager has something no modern laboratory can manufacture quickly. 49 years of travel time. That may be the rarest resource in the entire mission. You can build a better detector. You can build a faster computer. You can build a larger antenna. You cannot instantly place any of them 25 billion kilometers away. Voyager's location took history to create, and that is why its age is not merely a weakness. It is also an asset. The spacecraft has been moving outward long enough to cross physical regions that younger missions have never reached. Its technology is old. Its location is new. That contrast makes Voyager almost unique in the history of exploration. Usually, our most distant scientific instruments are also our most advanced. Voyager reverses that expectation. It carries electronics from the 1970s into an environment being measured directly for the first time. Some of its remaining hardware was designed before personal computers became common, before GPS, before the World Wide Web, before thousands of exoplanets were known, before the first space shuttle launch, before many of the scientists now working on the mission were born. The spacecraft crossed Jupiter when Jimmy Carter was President of the United States. It crossed Saturn before the first Macintosh computer existed. It crossed the heliopause in an era of smartphones. It is still operating in 2026. The technological history of Earth has transformed behind it, while Voyager itself has changed only through commands, aging, failures, and deliberate shutdowns. That creates an odd temporal effect. Voyager is physically moving into the future while carrying the engineering past. Its computers do not become more modern as it travels farther. Its materials do not update. Every new measurement comes from the same basic machine that left Earth almost half a century ago. The data are new. The messenger is old. And in some ways, that makes Voyager's current location even harder to grasp. We often understand distance through travel time. A flight lasts hours. A road trip lasts days. A voyage across an ocean lasts weeks. Voyager has been traveling continuously for nearly 49 years. But even that description hides something. The spacecraft did not spend 49 years going to its current location in the way an airplane goes to a destination. There was never a point labelled 2026 Voyager position waiting for it. Its location is simply where constant motion has placed it after nearly 5 decades. Next year, that answer will be different. 10 years later, if the spacecraft survives physically, different again. The question, where is Voyager 1, therefore has no permanent answer, only a moving one. And that movement leads to another threshold that sounds almost impossible despite being very close in astronomical terms. In November 2026, Voyager 1 is expected to be 1 full light day from Earth. For the first time, a human-made object will occupy a location from which light itself needs an entire day to reach us. That milestone changes nothing about the spacecraft physically. There is no boundary there. no new environment, no scientific transition. But for us, it creates one of the clearest ways to understand the distance. Because after that moment, Voyager will no longer just be billions of kilometers away. It will be tomorrow away. One light day sounds almost modest beside a light year. It is not. Light can circle Earth more than 7 times in a single second. It can travel from the Moon to Earth in a little over 1 second. It can cross the average distance from the Sun to Earth in about 8 minutes and 20 seconds. Voyager 1 has pushed that same signal delay toward an entire day. By the time the spacecraft reaches the 1 light day mark, a message sent from Earth on Monday would not arrive until Tuesday. If Voyager replied immediately, Earth would not hear that answer until Wednesday. That is what distance has done to communication. It has turned a machine designed for command and response engineering into something closer to correspondence. You send instructions. You wait. You do not know what has happened yet. Then the past comes back. This delay is one of the cleanest demonstrations of relativity in ordinary operational life. Nothing is wrong with the radio. Nothing is slowing the signal below its natural speed. The signal is moving as fast as information can move through vacuum. The universe is simply too large. That distinction matters. If Voyager's radio equipment became infinitely powerful, the delay would remain. If NASA built an antenna 10 times larger, the delay would remain. If the signal were perfectly clean and impossible to lose, the delay would remain. Communication cannot outrun light. So every additional kilometer Voyager travels creates a permanent increase in the minimum time needed for Earth to know what is happening there. The spacecraft is moving only about 17 kilometers per second, tiny compared with light's roughly 300,000 kilometers per second. But it never stops. Every day Voyager adds more than 1 million kilometers to the separation. That means every year adds several minutes to the one-way light time. The delay grows slowly enough that mission teams can adapt, but relentlessly enough that the character of operations changes across decades. At Jupiter, command delays were measured in tens of minutes. At Saturn, in the outer heliosphere, now, nearly a day. Future interstellar missions would face the same problem, only more severely. At 1 light year, a command requires 1 year to arrive. A response requires another. At Alpha Centauri, the simple round-trip exchange would take more than 8 years. No communication system can solve that through greater power. Only autonomy can. This is why Voyager, despite being technologically ancient, points toward one of the central problems of future interstellar exploration. A true interstellar probe cannot be remotely operated in anything resembling real time. It must make decisions locally. It must detect faults, choose priorities, protect itself, decide what data matter, potentially navigate without waiting for Earth. Voyager was never designed for that scale of independence. Yet its enormous communication delay has forced the mission team to operate in a primitive version of the same regime. Commands are planned carefully. Sequences are checked repeatedly. Engineers anticipate possible outcomes before transmitting. A mistake cannot be instantly corrected. And when a fault occurs, the first challenge is often simply determining what happened almost a day earlier. That is why the spacecraft's continued survival feels less like keeping an appliance running and more like managing an expedition that is physically beyond immediate reach. Except Voyager has no crew, no hands, no eyes capable of improvisation, only hardware, software, and instructions. There is another consequence of the light time delay that is easy to miss. When NASA tells us where Voyager 1 is now, there are actually multiple meanings of now. There is the spacecraft's calculated present position. There is the position from which its most recently received signal was transmitted. There is the position it occupied when some measurement occurred. And there is the position Earth sees through any electromagnetic information arriving at this moment. Those are not identical. Suppose Voyager sends a measurement from nearly 1 light day away. By the time that measurement reaches Earth, Voyager has travelled roughly another 1.5 million kilometres. So the signal describes a location the spacecraft has already left behind. Mission navigation solves this mathematically. Engineers know Voyager's trajectory well enough to propagate its motion forward. They can calculate where it should be when a command arrives. They can compensate for Earth's movement. They can account for the spacecraft's velocity. But physically, every observation is delayed. We never experience Voyager's present directly. We reconstruct it. That is true for astronomy in general. When you look at the Moon, you see it about 1 second ago. The Sun, 8 minutes ago. Jupiter, tens of minutes ago depending on orbital geometry. The nearest stars, years ago. Distant galaxies, millions or billions of years ago. Voyager now occupies a remarkable middle ground. It is close enough to remain a machine we actively command, yet far enough away that interacting with it begins to resemble astronomy. We receive information from its past. We infer its present. That may be one of the most profound changes distance has made to the mission. Voyager began as a spacecraft we sent somewhere. Now it is becoming an astronomical object we communicate with. And the 1 light day threshold gives that transition a human scale. A day is familiar. Everyone understands a day. 25 billion kilometers is abstract. 170 astronomical units is abstract. A light day is immediate. Send a command before breakfast. It arrives the next morning. Wait for a reply. Another day passes. Suddenly, the geometry becomes emotional. Not because anything dangerous happens at 1 light day. Nothing does. But because it reveals how far Voyager has separated from the rhythm of life on Earth. We live in seconds and minutes. Voyager now lives in delayed days. And that separation is only increasing. If the spacecraft somehow remained operational for another 10 years, the delay would continue growing. Another 20. Farther still. Eventually, every troubleshooting cycle would stretch even longer. But communication delay is not the only way to measure Voyager's isolation. There is also sunlight. At Earth's distance, sunlight delivers about 1,361 watts of power to every square meter facing the Sun above our atmosphere. At Voyager's distance, the intensity falls by the square of the distance. At around 171 AU, sunlight is tens of thousands of times weaker. The Sun is still visually bright, but energetically, its light has become almost irrelevant to the spacecraft. This is why solar panels were never a realistic solution for Voyager's deep space mission. A panel that works near Earth would produce only a tiny fraction of that power at Voyager's current location. To collect the same solar energy, the array would need to become enormous. Voyager instead carries its own decaying heat source. That choice made the mission possible. But it also means the spacecraft exists in a curious state. The Sun still controls its large-scale gravitational history. The Sun still appears as the brightest star in its sky. Solar disturbances can still propagate outward and affect plasma around it. Yet ordinary sunlight can no longer sustain it. Voyager is physically connected to the Sun, energetically independent from sunlight, and environmentally outside the solar wind. 3 different meanings of solar influence, all producing different answers. This is why simple statements like Voyager has left the solar system can become misleading. Which solar system? The planetary system? Yes. The heliosphere? Yes. The Sun's gravitational domain? Not really. The Oort cloud? Not even close. The Sun's place in the galaxy? Voyager shares that. The boundaries overlap only in language, not in physics. And the farther Voyager travels, the more those distinctions matter. Because after 1 light day, The next great distances are not measured in days. They are measured in months, then years, and Voyager will never reach those scales as an active spacecraft. Its power will disappear first. Its signal will end first. Its mission will become history first, but its trajectory will keep carrying it outward long after the last command from Earth has become impossible to answer. And that raises one final practical question. If Voyager eventually goes silent, how will we know where it is after that? After Voyager 1 goes silent, its location will not become unknowable overnight. The spacecraft will stop talking. The mathematics will not. By the time communication ends, mission navigators will know Voyager's position, velocity, and trajectory with extraordinary precision. They will know how fast it is moving relative to the Sun. They will know the direction of that motion. They will know the gravitational environment surrounding it well enough to project the path forward. So even without another radio signal, Voyager's future position can be calculated. For a while, very accurately. Then, with slowly growing uncertainty. This is possible because Voyager is not maneuvering continuously. Most of the dramatic trajectory changes in its life happened decades ago during close planetary encounters. Jupiter bent the path. Saturn bent it again. After that, Voyager entered a much quieter gravitational regime. Its tiny attitude control thrusters can change orientation, but they do not significantly reshape its interstellar trajectory. Once the spacecraft becomes fully inactive, even those small adjustments will end. Voyager will become almost purely ballistic. Gravity will do the rest. That makes its future motion easier to model than that of an active spacecraft constantly performing large propulsion maneuvers. The Sun will continue pulling on it. Nearby stars will exert tiny forces. The Milky Way's gravitational field will influence its long-term path. But over decades and centuries, those forces can be calculated well enough to estimate where Voyager should be. The strange part is that after the radio dies, the spacecraft may still be detectable in principle. Just not easily. Voyager does not stop reflecting light because its transmitter fails. It does not stop interacting with electromagnetic radiation. In theory, a sufficiently capable telescope or radar system could try to detect it. In practice, the problem is brutal. Voyager is only a few meters across. It is more than 25 billion kilometers away. It produces almost no visible light of its own. Sunlight reaching it is already extremely weak, and the tiny amount reflected back toward Earth would spread over another enormous distance. It is not merely faint. It is competing with a universe full of background sources while occupying an extremely small angular target. The spacecraft's radio transmitter makes it easy to identify because Voyager actively announces itself at a known frequency and from a known direction. Take that transmitter away, and Voyager becomes a tiny dark object in a vast sky. Tracking it optically would be completely different from listening to its beacon. So the practical method after silence is prediction. We will know where Voyager is because we knew where it was before contact ended. This is not unusual in astronomy. Many objects are not continuously observed. Asteroids disappear behind the Sun. Comets move beyond useful detection. Spacecraft enter communication gaps. Their trajectories are propagated forward until observations resume. Voyager would simply become the most extreme version of that process. Except there may never be another observation. At some point, its calculated position could become more meaningful than any direct measurement. Humanity might say Voyager should be here, then centuries later, here. Then, tens of thousands of years later, somewhere in this region. As time grows, uncertainty grows with it. A tiny uncertainty in velocity does not matter much over one day. Over 1 year. It matters more. Over 10,000 years, even an extremely small error can become a substantial positional uncertainty. This is one of the central rules of long-term prediction. Small errors accumulate. Imagine Voyager's velocity is uncertain by only a tiny fraction of a meter per second. Over a few seconds, irrelevant. Over millions of seconds, measurable. Over billions of seconds, large. Now add uncertainties in the motions and masses of stars the spacecraft may pass. Add the galaxy's gravitational structure. Add unknown small objects. Add forces so weak that they are meaningless today but persistent over geological time. Evil, the future path becomes a widening corridor rather than a razor-thin line. That does not mean Voyager could suddenly turn around. It does not mean the spacecraft might secretly return to Earth. The large-scale outcome remains stable. Voyager is escaping the Sun. It is entering a long galactic orbit. But its exact future coordinates become increasingly uncertain. And this reveals another difference between an interstellar probe and a planet. Planets are massive, bright, and regularly observable. Voyager is tiny. Once its beacon is gone, there may be no practical reason to spend enormous observatory resources trying to recover it. Its scientific mission will already have ended. Its location will become historical rather than operational. That is an extraordinary transition for an object that has been monitored continuously for so long. For almost half a century, Voyager has existed inside a system of human attention. Engineers receive telemetry, scientists examine data, antennas schedule contact, commands are planned, faults are diagnosed. Every major change becomes a mission event. Then someday, that attention will become one way. Earth may continue calculating. Voyager will no longer respond. Eventually, even the mission team itself will disappear. Not because something failed, because generations pass. The people who designed Voyager were already replaced by younger engineers. Those engineers will be replaced again. Mission documentation will outlive individuals. Archives will outlive teams. The spacecraft may outlive the institutions operating it. That is when "Where is Voyager?" changes from a question for flight controllers into a question for historians and astronomers. And perhaps, much later, archaeologists of technology. This future has an unusual precedent. Pioneer 10 and Pioneer 11 were earlier spacecraft placed on escape trajectories from the solar system. Both eventually became too weak to communicate reliably. Pioneer 10's final useful telemetry was received in 2002, with a last extremely weak signal detected in 2003. The spacecraft did not cease to exist when Earth stopped hearing it. It simply crossed from active mission into predicted trajectory. Pioneer 11 had done the same years earlier. Today, neither spacecraft is operating. Yet their approximate paths through the galaxy can still be calculated. Voyager 1 will eventually join them. The difference is how much farther Voyager will have travelled before silence, and how much information it will have returned on the way. There is something almost counterintuitive here. We often think communication defines whether a spacecraft is present. When the signal disappears, the mission feels gone. Physically, almost nothing changes at the moment of radio silence. The spacecraft is still there. Its antenna is still there. Its golden record is still there. Its structure still carries the marks of launch, planetary encounters, radiation exposure, and decades of interstellar flight. Only the relationship has changed. Before silence, Voyager is a remote participant in human science. After silence, it is an object with a human origin but no active connection to humanity. And even then, it keeps moving at nearly the same tremendous speed. 17 kilometers every second. More than 60,000 kilometers every hour. Roughly 1.5 million kilometers each day. Nearly 500 million kilometers each year. The numbers continue even when nobody is receiving them. That is perhaps the most important thing to understand about Voyager's future location. The mission has an ending. The trajectory does not. The spacecraft does not need power to coast. It does not need a working computer to remain on an escape path. It does not need an antenna pointed at Earth to continue moving through interstellar space. Newtonian motion carries on without an audience. So centuries after the last transmission, Voyager will be farther away. Thousands of years later, farther still. Tens of thousands of years later, it will pass through the broad neighborhood of another star. Millions of years later, the Sun and Voyager may occupy dramatically different regions of their galactic orbits. But even this enormous future does not answer one uncomfortable question. Could anything stop it? Could Voyager collide with something? Could a star capture it? Could it hit a planet? Could some future gravitational encounter throw it back toward a solar system? The answer is not impossible. But the probabilities are nothing like the images those questions create. Because interstellar space is not only enormous, it is almost impossibly sparse. And once we understand just how empty Voyager's road really is, we can estimate what its chances are of ever hitting anything again. The chance that Voyager 1 hits something substantial is extraordinarily small. Not zero, just small enough that human intuition is almost useless. We evolved in an environment where matter is everywhere. Air surrounds us, dust settles on surfaces, rain strikes the ground, objects collide constantly. Even an empty room is filled with molecules. Interstellar space is nothing like that. There are particles out there, gas atoms, dust grains, cosmic rays, occasional larger fragments. But the distances between significant objects are so enormous that a spacecraft only a few meters across can travel for millions of years without coming remotely close to anything large. This is why Voyager can continue for so long after its mission ends. There is no atmospheric drag to stop it. No interstellar sea thick enough to slow it noticeably. No invisible resistance waiting to grind it to a halt. Each individual particle impact transfers momentum, but the surrounding matter is so sparse that the cumulative effect on Voyager's motion is negligible across ordinary astronomical timescales. Its speed will change mainly because of gravity, not friction. That is the first important correction. Voyager is not gradually coasting to a stop. There is no universal background medium that eventually brings moving objects to rest. Motion is relative. Once the spacecraft has escaped the Sun, it continues moving through the galaxy unless gravity redirects it or a collision changes its momentum. And a collision with something large is spectacularly unlikely. Consider stars. The Milky Way contains hundreds of billions of them, which sounds crowded. But spread those stars across a galactic disk tens of thousands of light-years wide and thousands of light-years thick, and the average separations become enormous. The nearest star system to the Sun is more than 4 light-years away. That is typical of the basic problem. Stars are large. Space between stars is incomparably larger. A probe could pass through the galaxy for an immense amount of time without ever coming close to a stellar surface. Even Gliese 445, Voyager 1's famous future encounter, will not come close in ordinary terms. A separation of about 1.6 light-years is vast. If the Sun were replaced by Gliese 445 at that distance, the spacecraft would still be nowhere near the star's planets, assuming it has any. Voyager would simply pass through the same broad galactic neighborhood. That encounter will not capture the spacecraft. It will not sling Voyager dramatically onto a new trajectory. The gravitational effect will be small because the separation remains so large. For a star to significantly alter Voyager's course, the spacecraft would have to pass much closer. And for a direct collision with a star, the geometry would have to become almost absurdly precise. A star can be more than 1 million kilometers across. That sounds huge. But compare that diameter with light-years of empty space. The target shrinks almost to nothing. Planets are even smaller. So the idea that Voyager might randomly strike an Earth-like world somewhere in the galaxy belongs more to fiction than probability. Not because planets are rare, We now know planets are common. But because planetary systems occupy tiny cross-sectional areas compared with the volume separating stars, Voyager would first need to pass through a planetary system closely enough, then cross the orbital distance of a planet at exactly the right time, then intersect that planet's actual position. Three-dimensional space makes the odds collapse. Asteroids and comets create the same problem. There may be vast numbers of small bodies between stars. Some may have been ejected from planetary systems. Interstellar objects like 1I Oumuamua and 2I Borisov prove that solid bodies do travel between stars. So Voyager is not the only wandering object in interstellar space. But many objects does not mean crowded. Even enormous populations can remain extremely sparse when distributed through galactic volumes. This is a recurring trap in astronomy. Count and density are not the same thing. A trillion rocks scattered through enough space can still leave almost all of that space empty. Voyager is much more likely to encounter microscopic material. Dust is real. Small grains can strike the spacecraft at high relative speed, and speed changes everything. A grain too small to notice on Earth can release significant energy when it hits at tens of kilometers per second. Over millions of years, repeated microscopic impacts could pit exposed surfaces and degrade materials. Larger grains would be more damaging. A sufficiently large collision could puncture or fragment part of the spacecraft. But predicting such an event is impossible because we do not have a detailed map of every grain along Voyager's future trajectory. The risk is statistical, and over enormous timescales, even tiny probabilities accumulate. That means Voyager's future is not guaranteed. It is merely likely to remain intact for a very long time. There is an important distinction there. People sometimes say Voyager could survive for billions of years. Physically, that is possible. But nobody can promise the spacecraft will remain pristine or fully recognizable for billions of years. Cosmic radiation will alter materials. Micrometeoroid impacts will accumulate. Thermal conditions will change as Voyager moves through different galactic environments. A rare larger collision could destroy part of the structure. And over sufficiently long periods, the probability of a disruptive encounter becomes harder to dismiss. Still, the spacecraft has one enormous advantage: its size. Voyager is tiny compared with astronomical structures. A star crossing a dense region may gravitationally interact with many objects because its mass influences an enormous volume around it. Voyager does not. It has almost no gravitational reach of its own. It is effectively a passive test particle. That means it does not pull other objects toward itself in any meaningful way. Nothing is seeking it. Nothing is orbiting it. There is no gravitational funnel increasing its collision cross-section. It simply passes through whatever volume its trajectory intersects. That volume is narrow. Very narrow. This is why Voyager's odds of striking a planet are so fantastically low, even over geological time. But gravity could still change its future without a collision. A sufficiently close stellar passage could bend its path. The physics is the same basic principle that Jupiter and Saturn used during Voyager's active mission. Gravity changes velocity. But the geometry would need to be much more favorable than the currently predicted Gliese 445 passage. A close star could accelerate Voyager relative to one reference frame, slow it relative to another, or redirect it onto a different galactic orbit. Over billions of years, repeated stellar encounters could gradually alter the trajectory. That is why saying Voyager will follow its present path forever is not physically precise. Its path is predictable now. Its broad escape from the Sun is secure. Its exact trajectory across deep time is not immutable. The galaxy is gravitationally alive. Stars move past one another. Molecular clouds add mass concentrations. The galactic disk exerts a collective gravitational field. Voyager is embedded in all of it. There is even a remote possibility that a future encounter could place Voyager onto a path that passes through another planetary system. But remote is the important word. Nothing in the known trajectory points towards such an event. The spacecraft is not secretly headed for an inhabited world. It is not on a timetable to enter another solar system. Its known future is mostly empty distance. That emptiness is part of what makes the golden record so symbolic. The record was not launched because anyone expected interception. It was launched despite the likelihood that nobody would ever find it. A message sent into a medium where almost nothing happens. A gesture made against astronomical probability. And that may be the deepest difference between Voyager as engineering and Voyager as culture. Engineering asks whether the spacecraft can survive. Science asks what it can measure. Navigation asks where it will go. The golden record asks whether meaning still matters when the probability of an audience approaches zero. But before Voyager becomes only a silent artifact, there is one more misconception worth removing. People often imagine that because Voyager 1 is the farthest human-made object, it must also be the fastest spacecraft ever launched. That is not true. And understanding why reveals one final trick of orbital mechanics. The difference between being fastest now, moving fastest at one moment, and simply having had the longest head start. Voyager 1 is not the fastest spacecraft humanity has ever built. That title belongs elsewhere. Spacecraft such as Parker Solar Probe have reached far higher speeds than Voyager by diving deep into the Sun's gravitational well, near perihelion. Parker can move at hundreds of kilometers per second relative to the Sun, vastly faster than Voyager's roughly 17 kilometers per second. So why is Voyager still the farthest? Because speed alone is not enough. Direction matters. Trajectory matters. And time matters. Parker Solar Probe becomes extraordinarily fast because it falls toward the Sun. The Sun's gravity accelerates it as it approaches, and then Parker climbs away again along its elongated orbit. Its enormous peak speed does not mean it is escaping the solar system. Voyager 1 is doing something completely different. It is moving outward on an escape trajectory. That outward motion has continued for nearly 49 years. No dramatic perihelion speed burst. No return loop. Just relentless separation. That is the advantage of a head start measured in decades. A newer spacecraft could travel much faster for part of its mission and still remain far behind Voyager in total distance from Earth and the Sun. This distinction between instantaneous speed and long-term displacement appears everywhere in orbital mechanics. A spacecraft can be extremely fast while moving around a bound orbit. Another can be slower but moving permanently outward. The first may win the speed record. The second wins the distance race. Voyager 1 is the second, and its current speed is the result of everything that happened early in the mission. The launch vehicle gave Voyager its initial energy. Jupiter's gravity assist increased its heliocentric speed. Saturn changed its direction and helped place it on the final escape trajectory. After that, no giant engine kept pushing. Voyager has mostly been coasting. That word can make the journey sound passive. It is not. Coasting through a gravitational field is still motion governed by physics every second. As Voyager climbs away from the Sun, solar gravity continues pulling backward on it. That means its speed relative to the Sun gradually decreases. The spacecraft is escaping, but it is not moving at exactly the same speed forever. The Sun is still taking a little speed away as Voyager climbs out of its gravitational potential well. The key is that it cannot take enough away to stop the escape. Voyager has positive orbital energy relative to the Sun. Its trajectory is open. That is what separates escape from a very large ellipse. If Voyager were moving slightly more slowly, the Sun could eventually bend its path into a bound orbit. It might travel enormously far outward, slow down, reach an aphelion, then begin falling back. That is not Voyager 1's future. It is above solar escape velocity for its trajectory. The sun can slow it. It cannot reclaim it. Eventually, as the spacecraft moves farther away and the sun's gravitational influence weakens, Voyager's speed relative to the sun approaches a more nearly constant asymptotic value. That final escape speed is lower than the speed it had closer to the sun, but still enough to carry it indefinitely outward from the solar system. This gives us another useful way to understand Voyager's present position. It is not merely far away. It is dynamically gone. There is a difference between being distant and being unbound. A comet can travel hundreds or thousands of astronomical units from the sun and still be gravitationally bound, destined to return eventually. Voyager is much closer than many possible Oort cloud orbits, but Voyager is escaping. Distance alone does not tell you whether something belongs to the solar system dynamically. Energy does. This is one of the reasons the Oort cloud creates so much confusion in discussions about Voyager. A comet in the distant Oort cloud might be tens of thousands of astronomical units away and still orbit the sun. Voyager, at around 171 AU, is vastly closer, yet already on a hyperbolic escape trajectory. So which one is more outside? The answer depends on what outside means. Geometrically, the comet may be much farther away. Dynamically, Voyager is leaving permanently. Environmentally, Voyager is already beyond the heliopause. The same object can cross one definition of a boundary long before another. There is no single edge. That becomes even clearer when we compare Voyager with New Horizons. New Horizons launched in 2006. It left Earth on an extremely fast departure and reached Pluto in less than 10 years. For a mission covering that initial distance, it was extraordinarily efficient. But New Horizons did not receive the same cumulative gravity assist history that Voyager 1 did. It used Jupiter for a major assist, but its final outward speed remains lower than Voyager 1's. And Voyager already had almost 3 decades of head start. So New Horizons will not simply catch Voyager, not on their current trajectories. Voyager's distance lead keeps the older machine in front. This can feel wrong because technology usually works the other way. New aeroplanes outperform old aeroplanes. New computers outperform old computers. New rockets can outperform old rockets. But deep space distance rewards launch history. Once an object has been moving outward for decades, overtaking it becomes a serious propulsion problem. To catch Voyager, a future mission would have to leave the solar system substantially faster than Voyager and sustain that advantage long enough to erase a lead of tens of billions of kilometers. That is possible in principle, but it would require a mission designed for speed from the beginning. Gravity assists could help. A close solar O-berth maneuver could help even more. In an O-berth maneuver, a spacecraft performs a propulsion burn while moving extremely fast deep in a gravitational well, such as near the Sun. Because the spacecraft already has high kinetic energy, adding velocity there can produce an unusually large increase in orbital energy. In principle, a probe diving close to the Sun and firing a powerful stage at perihelion could leave the solar system much faster than Voyager. Laser-driven sails could go faster still if the engineering challenges were solved. Advanced nuclear or fusion concepts might eventually change the scale completely. But none of those technologies alters what Voyager represents. Voyager is not impressive because it is the theoretical limit of speed. It is impressive because ordinary chemical launch technology, combined with planetary gravity and time, carried a working spacecraft into interstellar space. That is a very different achievement, and it leads to a subtle question. If Voyager 1 is not the fastest spacecraft ever, could some future mission eventually overtake it and become the most distant human-made object? Yes. There is no physical reason Voyager must hold the record forever. A sufficiently fast interstellar probe could erase the distance gap. If humanity launches spacecraft capable of tens or hundreds of kilometers per second of sustained solar system escape velocity, Voyager's lead could eventually disappear. The interesting question would become when. Suppose a future probe escaped the Sun at twice Voyager's outward speed. It would still need decades to close a lead built over nearly half a century. At 3 or 4 times Voyager's speed, the catch-up time falls dramatically. At true interstellar probe velocities, Voyager's record could become temporary. But today, no launched spacecraft is on a trajectory that will soon overtake it. So Voyager remains first in distance, first across the heliopause, first to directly sample interstellar space along its path, and almost certainly the first human-made object to become 1 light day from Earth. That last milestone may be the most accessible of all, because it strips away the orbital mechanics. No gravity assists, no hyperbolic excess velocity, no heliopause definitions, just time. 1 full day for light. That is where 49 years of motion have carried a machine that began its journey on a launch pad in Florida. And when you compare that 1 light day with Voyager's entire future, another strange realization appears. The spacecraft has spent nearly half a century traveling outward. Yet almost every dramatic event in its known future lies tens of thousands, millions, or billions of years away. Voyager's active story is reaching its end. Its physical story is barely beginning, which means the final answer to where Voyager 1 is right now cannot be only a location. It has to be a position between 2 times. Behind it, 49 years of human engineering, planetary encounters, failures, repairs, and signals. Ahead of it, almost unimaginable silence. That silence is coming. Not tomorrow, not on a date anyone can guarantee, but it is built into Voyager 1's physics. Every year, its electrical margin shrinks. Every surviving subsystem becomes more precious. Every command from Earth travels farther before it arrives. Every reply begins its return journey from a spacecraft that is older, colder, weaker, and more isolated than it was the year before. Eventually, something will give. Maybe power, maybe communications, maybe attitude control, maybe a component that has already survived far beyond its intended lifetime. When that happens, Voyager 1 will stop being an active mission. But nothing about its trajectory will suddenly change. It will still be moving at roughly 17 kilometers per second, still heading away from the Sun, still carrying the golden record, still embedded in the local interstellar medium, still following a galactic path whose next remotely notable stellar passage lies tens of thousands of years away. The most distant machine we have ever operated will simply become the most distant machine we can no longer operate. And that may be the cleanest answer to the question we started with. Where is Voyager 1 right now, after almost 49 years in space? It is more than 25 billion kilometers from Earth, roughly 171 astronomical units from the Sun, far beyond Neptune, far beyond Pluto's average orbit, beyond the termination shock, beyond the heliopause, inside interstellar space, moving northward out of the plane where the major planets orbit, travelling outward at roughly 17 kilometers per second, nearly 1 light day from Earth, still alive, still transmitting, still measuring an environment no other active spacecraft occupies along that path. But even that summary can hide what those numbers really mean. 25 billion kilometers is not just a distance. It is a communication delay, a power problem, a navigation problem, a scientific opportunity, a historical record, and a scale lesson. Voyager has travelled farther than anything humans have ever built, yet on the scale of the stars it is still almost beside us. That may be the most important realization in the entire mission. Voyager feels impossibly remote because our civilization is small. The galaxy makes Voyager look local. If the Sun and Voyager were plotted on a map of the Milky Way large enough to show the nearest stars clearly, the 2 points would be almost indistinguishable. 49 years of continuous motion barely separate them on that scale. This is not evidence that Voyager failed to go far. It is evidence that space is much larger than our intuition can comfortably hold. The spacecraft crossed Jupiter in less than 2 years after launch, Saturn in just over 3. It took decades more to reach the heliopause, and reaching another star would require tens of thousands of years. Each step outward reveals another layer of scale. Planetary distance, heliospheric distance, interstellar distance, galactic distance. The units change because ordinary language stops working. Kilometers become awkward. Astronomical units become better. Then light days. Eventually, light years. Voyager has spent almost half a century climbing that ladder, and it is still near the bottom. There is a temptation to see that as discouraging. If our fastest long-lived interstellar artifact has moved only about 1 light day away after nearly 5 decades, what hope is there of reaching another star? But Voyager was never designed to answer that question. It was designed with 1970s technology to visit the outer planets. Everything after that became extra. The engineers who built it did not have modern processors. They did not have modern materials. They did not have advanced autonomous navigation. They did not have laser propulsion. They did not have decades of exoplanet discoveries motivating direct interstellar exploration. They had chemical rockets, gravity assists, radioisotope power, a 3.7-meter antenna, computers primitive by modern standards, and extraordinary trajectory design. That was enough to reach interstellar space. Not another star, but the region between stars. Those are different achievements. Voyager proved that a functioning machine could cross the heliopause. It proved that instruments built for planetary exploration could survive long enough to measure the local interstellar medium. It proved that spacecraft software could be repaired across tens of billions of kilometers. It proved that a radio signal measured in tens of watts could still be recovered after nearly a day of light travel. It proved that engineering margins can be stretched across generations. Most importantly, Voyager transformed interstellar space from an inferred environment into a directly sampled one. Before Voyager, the heliopause was a predicted frontier. After Voyager, it became a measured crossing. That shift is easy to overlook because the event produced no photograph, no dramatic landscape, no alien world. The discovery appeared as changes in particle counts, magnetic fields, plasma density, and radio data. But scientifically, that is what exploration often looks like. A line on a graph changes, a frequency shifts, a signal disappears, another rises, and suddenly humanity knows that a boundary billions of kilometers away is real. Voyager's current location is valuable for the same reason. It is not spectacular because of what a camera would see. It is spectacular because of where the sensors are. The spacecraft sits beyond the protective bubble created by the sun's wind, measuring the galactic environment directly. Every surviving reading answers a question that cannot be answered in quite the same way from Earth. That is why mission engineers keep fighting for watts. Why they shut down instruments strategically instead of abandoning the spacecraft. Why ancient software is still being studied. Why giant antennas continue listening. The science is happening at a location that took 49 years to reach. That location cannot be replaced quickly. There is another consequence. Voyager 1 has become a measuring stick for our technological civilization. When it launched in 1977, the spacecraft represented the edge of what humans could send outward. Today, our technology is vastly more advanced, but Voyager itself remains farther away than all of it. That creates a strange inversion. The old machine occupies the new frontier. Modern spacecraft may have better computers, better cameras, better propulsion systems, better instruments, and better autonomy. But they do not have Voyager's distance. Not yet. Time has become part of the hardware. You cannot manufacture 49 years of travel. You have to wait for it. That is why Voyager's record may survive longer than many technological records normally do. Not because nobody can build something faster, because catching a decades-old head start across the solar system is difficult. Someday, another spacecraft may pass it. That would not diminish Voyager. It would mean Voyager helped define the distance worth surpassing. The same pattern has happened throughout exploration. One ship crosses an ocean. Another goes farther. One aircraft breaks a speed barrier. Another exceeds it. One spacecraft reaches interstellar space. Eventually another should go faster, farther, and with instruments designed specifically for that environment. When that happens, Voyager will become less unique scientifically, but never historically, because there can only be one first object from Earth to cross that boundary, and Voyager 1 already did it. So imagine the spacecraft one last time. Not as the polished model displayed in mission graphics, not surrounded by colourful nebulae, not passing close to some giant alien planet. See it as it really is. A small machine, a dish antenna, a long magnetometer boom, instrument housings, 3 aging radioisotope generators, no engine burning continuously behind it, no visible trail, no dramatic destination ahead, just momentum, black space, starlight, sparse interstellar matter, and somewhere far behind, a star called the Sun. Near that star is a planet too small to see. On that planet, giant antennas are still listening. A signal arrives. It began its journey nearly a day earlier. Inside that signal are measurements from a place no human being has visited and no other active spacecraft occupies along Voyager's path. Then Earth sends another command. The radio wave leaves the antenna, passes the Moon, crosses the orbit of Mars, continues beyond Jupiter, beyond Saturn, beyond Uranus, beyond Neptune, across the enormous darkness outside the planets, past the region where the solar wind became turbulent, past the termination shock, across the heliosheath, through the heliopause, and eventually, almost a day later, it reaches a machine launched when much of the technology surrounding us today did not exist. Voyager responds, and for a little longer, the line remains open. That is where Voyager 1 is right now. Not at another star, not outside the Milky Way, not at the end of the solar system in every possible meaning of that phrase. It is just beyond the Sun's heliosphere, roughly 1 light day from Earth, moving through interstellar space while remaining extraordinarily close to home by galactic standards. Far enough to redefine human exploration, close enough that the stars have barely begun. And after almost 49 years, Voyager 1 is still doing the one thing it has done since 1977. Going farther,